So as we know, most of people who live in Cambridge, that there are a lot of tourists during summer in the streets of Cambridge. And although they take a picture of the same building, for example, they all use different cameras and different angles. So the intention is the same, but they all go home with a different image. And although the physics behind MRI is obviously very different, conceptually, it's similar that different parameters have, and different scanners have an effect on the image quality. And some sources of variation we have are, for example, the magnitude or number of B values. So for example, higher B values are associated with reducing diffusion metrics, or if we have a multi-shell acquisition, that could reduce also noise. Another example is obviously the angular resolution. So the more directions you have, the better maybe your contrast between gray and white matter on FA maps. Whereas, for example, on the MD maps, this might have not as of a drastic effect. Likewise, it could could improve signal to noise ratio and help to recover the orientation density function. So you get a clearer signal if you have like more directions. Also, spatial resolution field strength has obviously also an effect. So larger voxel size were associated with decreased FA, but increased MD, and increased field strength could, for example, increase FA in highly organized white matter structures. But why would we bother about
Sorry
data?
to interrupt.
Yeah.
Sorry, we've got a very significant delay, I think,
Okay.
mostly on your slides.
Okay.
Oh, is it just us? Oh, okay. So it seems to be the problem is just us here in the lecture theatre.
Okay. Maybe you can just have a quick pause in between the slides and you let me know if you see it. So do you see the, why do we want to harmonize data?
Screen now. At the moment, we're still looking at the slide with examples of sources of variation, and it's just that your boxes are just very slowly coming through now.
Oh.
Yeah, so we're just going to suggest if you could start the presentation again.
Okay.
Yeah.
Sorry about this.
Yeah, I think it seems to be fine on, and there's just a problem here in the lecture theatre, Stefan. So I think the problem may be as much ours as.
Can we restart?
I'm sorry, I'm not sure what I should do about it, to be honest. Can you see my slide, the very first slide again?
Can you escape?
Have you tried sharing again?
Parameters and on the same scanner and everything to avoid basically the scanner bias or this intersite biases. As we know in medical imaging, data is quite scarce, and we want to include data from multiple centers to boost basic statistical power and to find things in our clinical cohort. And this could be both retrospective, where we have already acquired data, or prospective, where we set up like a multi-center study, like comparable acquisition schemes. But also, we have nowadays lots of different population studies like UK Biobank or CamCan, and we want to leverage basically this huge data set, maybe to find something out about our clinical cohort, which might be smaller. For example, modeling a normal state of the brain, and then you could apply that maybe to disease spread and brains and see how the difference would be. And without harmonization, if you would just pull them together, you might have like such high interscanner variation that the subtle differences between your groups, for example, controls versus patients, might not be observable anymore. So that's why you want to do harmonization. And also, as John said in his previous talk, that machine learning models, for example, overfit quite easily. And if you have like a prediction task where you want to predict, for example, the outcome of patients, then if you have site-specific biases which correlate with the outcome, then maybe your model just sticks to the site-specific bias rather than finding actually anything interesting about the disease. So you do want to harmonize, but what methods do we have to harmonize our diffusion data? One quite popular method is COMBAT, which has been introduced for genetic data, but was later on adapted for diffusion MRI harmonization, but also for cortical thickness harmonization, for example. And the main idea is that you have two different distributions that represent the difference in the scanners, and you try to model this statistically by having one additive factor and one multiplicative factor that basically shift your signal in a way that you can account for these differences between scanners. The neat thing about this method is that you can also include confounding factors. So for example, if you have different cohorts like patients or controls and also like different ages and sex and maybe other clinical variables, you can include that. So that these are not reduced basically. So you don't eliminate the variable of interest and just the scanner bias. And they could actually show that the percentage of significant voxels, when you look at different sites, was quite reduced when you use COMBAT. So I don't go into all these different methods, but scaling would be just your set scoring. So you can see that drastically reduced compared to raw data or set scoring. At the same time, if you have age as the variable of interest, you can see that this is basically retrieved when applying COMBAT better than, for example, when you just use the raw data or the scaling. Another method, like a lot of other methods, rely on spherical harmonics. So I want to briefly introduce that for people who don't know what that is. Basically, you have a spherical harmonic expansion where you have different bases of spherical harmonics, and with different coefficients, you can weight your bases in a way that you can represent your diffusion signal. So it's just a different representation of your signal. Usually what people do is compute rotational invariant spherical harmonics, short RISH, and that's literally nothing else but using the coefficients that you found by estimating the signal and basically square them and sum them up for different orders. And one quite popular tool to harmonize your data is linear RISH feature scaling. And initially this was introduced on a region-wise level, but later on expanded for voxel-wise harmonization. And the whole idea is basically that you first compute your RISH features, spatially normalize these for healthy controls that are representative for both your scanners, and then compute scaling maps, which are literally just basically the ratio basically. And then in the end, when you have these scaling maps for different scanners, you can back project your scaling map here back to your native space and just apply this to scale your signal again. And in the original paper, they've shown also like this example on two different scanners, where you have in the first row, you have one scanner, basically the RISH features. In the second row, you have the other scanner and the RISH features, and then you see the scaling maps, how this would compare. And they also showed before and after harmonization, basically you can reduce the bias between the different scanners. So blue and red are the ones that are harmonized. And interestingly is that they also analyzed how many healthy controls you would need to basically obtain a scaling map that is sufficient to reduce these scanner biases. And you can see like too few are not good enough, and they recommend actually to have something around 50 to 16 healthy controls that are also matched. So there should be somewhat like age matched and gender matched. Obviously, you have a lot of different machine learning approaches as well that can help to harmonize your data, and I want to provide a bit of an overview. So some methods work with traveling hats, where you just have the same patients scan or the same controls scanned on two different scanners, and And one approach is, for example, that you just use a convolutional neural network to scale between these different RISH features. And initially, this has been shown already to work to outperform also linear RISH feature scaling. And there have been multiple different approaches suggested, all based on convolutional neural networks. And one quite successful one is the FSCNet, basically. And this is just a few convolutional neural networks just to learn the mapping between two different scanners. But obviously there you need always traveling heads, and that might not be feasible for different studies. So there have been also efforts to basically alleviate this and create methods where you just look at, they have matched controls, but they don't have to be the exact same ones on both scanners, basically. And usually they are dependent on, for example, generative adversarial networks. But I want to specifically highlight one that is basically that you learn a scanner invariant representation of your signal via variational autoencoders. And that's a fairly recent paper. And the whole idea for this is basically that you have your RISH feature signal, and you basically feed it into an encoder and try to reconstruct it. So that's the whole idea of like an autoencoder, to reconstruct your image, but also compresses in the meantime. So SET, for example, would just keep the features that are important to represent your signal and gets rid of all the noise that's not important. And the neat thing about this is that the trick is that you include a variable S that would be your scanner variable. And by that, the decoder directly knows explicitly from which side your data comes, so that basically the encoder actually doesn't have to learn this. So the best compression of SET and the best use of it would be if it completely exclude any site-specific information, because we already explicitly name it here. And for that to make it work, you need a lot of different losses basically to train your network. And one is like the reconstruction loss, as I mentioned, basically just comparing the input and the output with one another. But you also compare, you also have like an adversarial loss, which basically just tries to predict based on your reconstruction if the scanner comes from one or the other side. So during your training, this would look like this, that you have like inputs from different sides, and you learn like a sideless set, including your S side effect basically, and try to reconstruct it. And during the test time, since you learned like the sideless set, you can just choose one specific side and then basically project your original data to one specific side. And that's quite neat because you could choose any side that you would want. But which algorithm should we use? Because there are so many out there. And there is like a challenge, there was a challenge to compare these different algorithms with one another. And deep learning was had quite a big potential. However, you can see also here that linear RISH feature scaling still outperforms all the other ones. And here you see the different deep learning methods in purple. And one quite important one was the previous one that I mentioned, the FSCNet or DIQT, that was quite good, but also this SH1 layer. So that has literally only one convolution neural network, one convolution layer. And the people who applied this model realized basically that your data gets just smooth. So it just blurs basically images. And that helps already to alleviate basically your interscanner bias. So although like these methods have all some potential, they might just smooth your data. And it seems like linear RISH feature scaling, although this seems like fairly straightforward method without any fancy machine learning models, still outperforms the other ones. To provide like a little bit of overview of like the three main methods I mentioned: combat, linear RISH feature scaling, deep learning. So combat is quite simple to apply. So that's useful when you have also a complex data set where you have like all different clinical variables, because you also can include confounding factors. The disadvantage of Combat is that it might require that you pre-process your data all in a similar way, because it has been shown already that when you process your data differently with different reconstruction models, that you might not be able to get rid of the scanner biases. For linear RISH feature scaling, it's relatively simple, and new sites can be fairly quickly integrated. If you have already a template, you just would register, spatial normalize your new data to this template, generate your scaling maps, and then basically can back project this again and scale your data. The problem is that you need fairly high amount of matched controls, which you might not always have depending on your study, obviously. And it's also registration based. And registration can be quite challenging if you have some pathology, for example. And while Combat, for example, uses FA or BMAP, whatever parameter map you want to use, linear RISH feature scaling obviously relies on the SH representation, and that's just a little bit more complicated one, another step to account for, rather than just Combat applying basically this model. Linear RISH feature scaling has been reported quite often to be better than Combat, and also like shown for different diseases to be successful to help get rid of the scanner bias and improve basically the findings for their clinical studies. Deep learning models are quite powerful, as we saw, and they can be much more quickly applied once they are trained. So we don't have to do anything in terms of spatial normalization. That can be just applied right away without any registration. So that's an advantage. But the problem is that they are often quite complicated to train, and we also still might need match controls. And in theory, if you have a new site, you always have to retrain your whole model, and that can obviously take quite a long time. And deep learning models often also based on RISH feature representation. So that's the same as linear RISH feature scaling, a bit maybe more complicated. But this last one that I described, the scanner invariant representation learning, that was reported to basically also outperform RISH feature scaling. So it seems like deep learning can really help to get rid of scanner biases, but it hasn't been validated as well as the other methods, maybe also because it's like fairly new. In conclusion, you have different approaches, but some are more or less validated. We are not 100% sure yet when you harmonize your data, if you actually introduce some biases as well. So we don't know if this might affect your clinical study either. And what they have shown also is that when you have a very different quality of your data, that you cannot harmonize your data to a better quality. So all your good quality data will be harmonized to the worst scanner quality, basically. They name this worst scanner syndrome. So this means if you have if you plan a multi-center study, you want to include only sites ideally that can acquire like high quality data, because otherwise this will be always a limitation. And it's not clear if we can ever get around this. One problem that is still open is how to scale this to multiple center sites. So if you have like 2 sites, it's always quite straightforward, but the more sites you have, the more complex it becomes. And for example, for linear RISH feature scaling, you would need to compute a scaling map for each of these different sites. And that means like 16 matched controls for all different sites. So it's probably quite complicated. And one future direction will be also, do we actually need image-to-image translation? So basically this harmonization, or if you want to do outcome prediction, might it be better to have some models that can generalize to different domains? For example, if you do segmentation or outcome prediction, maybe just learn models that take out the information of the scanner biases, but the scanner information, but still predict it. We wouldn't need to translate basically between the images, because for example, a deep learning model doesn't care what is in the latent space as long as you can get rid of your biases. So the take-home message is that you should have high quality data, because that makes your life easier. There are different algorithms, but it really depends on your data, whatever you have, depending on how different they are or how many match controls you have. Combat is quite simple, can be applied also to regions, and you can include confounding factors. Linear RISH feature scaling needs match controls, spatial normalization as well, but it's very well validated. So probably that's a good way to, good option to start with if you have enough controls. And deep learning models are very powerful, but still needs way more validation. So we don't harm our downstream task. These are the references, and that's it for me. If you have time, I'm ready for any questions.
Okay, thank you very much, Stefan. Can you hear me okay?
Yeah, I can hear you.
Okay, thank you very much. Any questions from the audience? Yeah, Rick Kenton, I'll take the microphone.
Thank you very much. In your overview table, you cited a paper by Moyer that said that deep learning outperformed RISH. But in your own results, I thought you showed that RISH did better than deep learning. Could you go back to your results table where you had some measure of...
Can you see that? I think there's still a delay.
Yes, sorry. I'm looking at, yes, I can.
Yeah, okay.
So I can see it now.
Okay, so
that paper's by Ning, I guess. So they can... Sorry, go ahead.
Yes, so exactly. So this paper is by Ning, right? The most recent one, where they showed basically also linear RISH feature scaling. In the original one, they didn't have linear RISH feature scaling. But here, you're right. I mentioned basically linear RISH feature scaling is much better than all the other deep learning models. But this paper was published before the other one, before the Moyer 2020. And they, in their paper, they used the same data because they collaborated also with Chantal Tax from Cardiff, basically, who also was part of the organizing team for the challenge. And there they showed basically that linear RISH feature scaling is not as good as theirs. So basically it's an update. So if you would like update this paper, you would maybe include that as well, the new variation and autoencoder model, and then maybe you have like a better, it would be somewhere here or whatever. So it just doesn't appear on this list because it hasn't been published beforehand. Yeah.
Okay. I was wondering what would combat look like on this kind of plot? Because in many situations we don't have matched controls. So I understand that combat would be the least we can do. But where would combat? I can't see the x-axis.
Yeah. So combat wasn't applied here either. Yeah. I think in Moyer 2020, in this one paper, they also showed combat and linear feature scaling and still outperformed both. And in the original paper from Kara Yumak, the people who introduced linear RISH feature scaling, they compared it to combat and they showed that it outperformed that. Obviously, you have to always take it with a pinch of salt because these people show their new method and try to sell their new method, right? So they, of course, show that it works better than other ones. And it really depends maybe on the data set. So I like combat for clinical data sets because you have the confounding variables. Usually you don't want to just you don't want to harmonize just healthy controls, right? You want to do it for like a clinical downstream task. So probably if you don't have matched controls, probably it's best to start with combat. But applying combat for different studies, I found mixed results sometimes. Sometimes it helped, sometimes it didn't. And even if it helped, it's not 100% sure if you still can get rid of all the scanner biases. But this holds also true for all the other methods as well. So I think it's the early stages. So we still don't know how much we can get rid of the scanner bias. Only because we reduce it doesn't mean they're still not there. Does this answer your question?
Thank you very much.